My name is Pam Maples, and I'm going to kind of follow up with what Bill said, and I'm going to, like he said, we didn't look at each other's presentations because of whatever reason, and I think mine is going to expand on his. Not necessarily follow it, but expand on it. So, here we go. Electricity. What is that stuff? So, this is an electron. It's a little red dot. I've drawn it very, very big so we can see it because electrons are microscopic in size. Electrons have a negative charge. It's a negatively charged particle of energy that spins around the outside of an atom. And like I said, it has a negative charge. And so we don't forget that. We'll draw him with a negative attitude as well. That way we'll recognize him when we see him. The electron moves through a wire, and it is the particle that makes electricity work. So the electron gives us the word electricity. So here's a stylized image of an atom, and you can see the nucleus right there in the center. And you can see these spinning balls, spinning orbits, and the little white balls are electrons. This happens to be an electron, or a diagram of an atom of copper. And if you take the atom, the three-dimensional picture, and smash it onto the screen, you're going to get something that looks like that. Nice and organized. And you can see that copper in the periodic table is element number 29, and the electrons are arranged in rings, and there's 2 electrons on the center ring, 8 on the next one, 18 on the next one, and only 1 hanging out here on the outside all by himself. And this is the electron that can move. They call it a valence electron, and this is the one that has the potential to move. If you disrupt it, it's not happy. You know, they're negative anyway, but it's really not happy out there by itself. It wishes there was something else there. So the electrons are negatively charged, and the neutrons, and the neutrons are kind of neutral, but the whole nucleus of the atom is positively charged overall, so it makes these electrons stick down close to it so they're just not flying all over the room. There's the periodic table, and there's copper, right there, number 29. And if you add these numbers up, they add up to 29. So the numbers on the periodic table indicate how many electrons are in the shell. So, electricity. To understand it, we can think about magnets. Everybody, hopefully, has played with magnets. If you place 2 magnets on a table with the north poles facing each other, like that, something's going to happen. A force, if you try to push them together, there's going to be this force that develops between them that doesn't want to let them go together. In fact, it will push them apart. If you let go, the magnets will fly apart. So in high school, we all learned that like poles or like charges repel. The north poles of the magnet are negatively charged. So like charges repel. So still thinking about magnets, if we put our magnets down with the north and south poles together, like that, and then let them go, they're going to suck themselves together, because what we learn in school, opposite poles, opposite charges attract each other. So here's our electron guy. And what would happen if we slide another one over there close to him? He doesn't like it very much. The negatively charged, they have the same charge. So if you apply the magnet principle, you get this field that generates up there between them that tries to push them apart. So the force that is pushing them apart is the force that makes our stuff run. That ability to not be near each other is what makes all of our electronic gadgets work. So here they are. They have the same charge. They don't like being that close to each other, but another way to visualize this force, if you're having trouble with just some imaginary force, try imagining it as a spring. It's a compressed spring between them, and they just don't like it, and so given a chance, they're going to move. They don't like being that close to each other, and they need to move away. So here we go, we're going to push them together. Really close together this time. Oh, the force gets huge. It creates a lot of tension between these guys. High tension, you've all heard of high tension wires? The spring now is much more compressed. It's so higher compression is higher voltage, higher tension, higher voltage. High tension wires are high voltage wires. Don't touch them. We all know tension. So why is this important? Those shouldn't be up there. Voltage is what we measure, so we know what we've got. What are we working with? What's it doing? What's it not doing? Why isn't it working? We measure the voltage. So another thing to think about on this slide is, why do we measure amperage in amps? And electric potential in volts. So we can measure volts, but we need to talk about what volts really are. And when you go and you measure the volts, what you're really measuring is the electric potential. So we'll demonstrate. If you put a bunch of these guys together in a box, you're going to have a battery. So we just load them up in there. Really, really full. All of these electron guys all have the same charge, and they're all trying very, very hard to get as far away from each other as possible. That creates pressure. So pressure can also be thought of as voltage. And voltage is almost universal substitute for the noun electric potential. Nobody says electric potential. They all say voltage. Amperage, in which we'll get to later, is the equivalent for current. And they don't really use current very much. Most people say amps. So pressure equals electric potential. If you have any volt battery, a 9-volt battery, 12-volt battery, any volt battery is simply electrons under pressure, the potential to do work. So that's why you get the potential, electric potential. These guys need to go somewhere. So pressure or voltage is what makes everything happen. There can be no electron flow without a difference in pressure. If you connect the battery to a circuit, and it's a circuit, by the way, because it's a circle. Here's our circuit. We'll stick a motor in there, and you can see that the switch is open. This is the switch. If you give the electrons a place to go, they are going to go. So with the switch open, electricity is waiting at the switch to move. Waiting there. If the switch is open, the voltage is said to be static. You could also think of that as stable voltage. The switch is open, it's stable, it's ready to go, it's not moving, it's not going anywhere. But as soon as you close the switch, things are going to begin to move. When a bunch of electrons are moving in a wire, it's called current. And another word for current is amperage, and we shorten that to amps quite often. So you've got your voltage in here, potential, pressure. The circuit is shut, closed, so now we have amps flowing. We use the amps to do the work. Sometimes you can think of the work as load. You see that in publications, the work or the load. Remember the motor? Without anything in that motor to slow down our movement here, it's going to go really, really fast and probably blow the fuse. So we need something to slow it down, and that is resistance. So here's our battery, our voltage, our potential moving, the motor. The job of resistance is to slow the current down, slow the amperage down, so the fuse won't blow. Resistance is measured in ohms. So we're going to stick some resistance in that motor, and then it goes much slower and is much more controlled. We don't have a fire, and things are good. Every load has resistance. A light bulb has resistance, and the excess energy is given off as light and heat. The coil wire from your car has resistance. That's how you're able to get such a big zap out of a 12-volt battery. Portable heaters have resistance, lots of it, because they get really, really hot, because they're heaters. And even the resistor in your computer on the motherboard, its job is to slow down the current, or the amps. So to sum that up, you've got voltage, which is pressure, pushing amperage, which is the current, through resistance to do work. That right there is electricity. The more the voltage is increased, the higher the amps get, and the faster the motor will turn. This right here is Ohm's law. And contrary to some people's popular belief, Ohm's law is a concept, not a math equation. Even though we write it like that, it's really just a concept. And the concept is, the more the voltage is increased, the more the amps will get higher, and the faster your motor will turn. Anyone in this room will tell you I hate math. Therefore, I like Ohm's law, because it's not math. Voltage, amperage, and resistance, they all work together to make our machines go. In a copper wire, all of the positive nuclei of the copper atoms, they're all nestled in there together, and all of the nuclei are stationary, and that preserves the shape of the metal, the shape of the wire. But the electrons can drift around from atom to atom. They're free to move. And as we know, they don't like each other. And since the electrons all have the same charge, when one electron moves, it pushes another. And I have drawn this out in a schematic here. This will be a wire. The green lines are the wire, and the wire is 1 atom tall. And for simplification, I've just put a plus and a negative here to represent our atoms. And if I shove an electron in from downstream, it's going to push that one, which is going to push that one, which is going to push that one, which is going to push that one. That's current. That's flow right there. Electron flow, or amps, happens close to the speed of light. You flick a switch, that light comes on. So we're going to talk about flow. There's 2 kinds of flow, and this will be the last time we talk about this particular kind of flow because we're focused on solar. But AC is alternating current, and it's drawn by this little sign. Current goes up, current goes down, current goes up, current goes down, on and on and on and on. And what it does is it reverses its polarity blazingly fast. You can't even see it. But some people, if you put an incandescent light bulb up and plug it in, some people have fast enough processors in their eyes that they can see that light blink. The refresh rate on a television is the same way. They can see that light blink. So this is the current that's in household power, AC. And if you're using solar panels and you have an inverter to invert your DC into AC, you can also, this is what kind of power you'll get. Direct current is moving from one pole to another. It's flowing in one direction, and this is the kind of flow that you commonly get from a battery. So electricity flows, current tends to flow from the negative to the positive. This side of the battery is more negatively charged than the other side. Due to a chemical reaction in the battery, the electrons here push the other electrons out into the wire. The flowing electrons are attracted to the positive side of the battery through the wire, and round they go. So we've just wired up a dead short, and it's just going to go round and round and round until it wears the battery out. Say this is a 6-volt battery. What that really means is there is an electrical potential difference of 6 volts between the positive side and the negative side. That's why they call it electrical potential. The battery is full of electrons that want to get far away from each other, but the potential for these particular electrons crammed in that little space is 6 volts. So here's our diagram. Got our battery, 6-volt battery, electrons under pressure, potential to do work. There they go. The amps is the amount of electrons flowing past any given point per second. And it's some crazy small number. But there they go. Look at them flowing past there. So we're measuring the amps right there is how fast it's going. So we put in our motor, our little engine. And the engine's got resistance in it, of course, because the ohms slow down the flow. And so it slows down the flow so that when the little motor wants to use the power, when the kid gets in there and flips the switch, vroom, off it goes, without like blowing up or melting down, because it has resistance. But wait, what is a watt? Webster says a watt is named for James Watt. Is equal to 1 joule per second. It shows the rate of energy transfer in respect to time. Whatever. A watt is a unit of power. And power is the rate at which energy is produced or consumed. Think of watts as a measure of electric flow. Does an electric device need a big flow or a small flow to work? For example, a 100-watt light bulb uses energy at a higher rate than a 60-watt bulb. This means that the 100-watt bulb needs a bigger flow to work. Likewise, the rate at which your solar energy system flows power into your home is measured in watts. A watt-hour is a unit of energy. It is a way to measure the amount of work performed or generated. So a watt-hour is the amount of work. Household appliances and other electrical devices perform work, and that work requires energy in the form of electricity. Power companies typically charge you for electrical energy by the kilowatt hour, which is equal to 1,000 watt-hours. So what's the difference? Watt-hours measure the amounts of energy for a specific period of time, and watts measure the rates of power at a moment in time. Those are words. I don't like words almost as much as I don't like math. So we're going to do it another way. A watt is a measure of power output. We all know the amount of light a 25-watt light bulb puts out. We all can visualize a 100-watt light bulb and the amount of light it puts out. And then there's the 750-watt street light bulb, very bright. Those are the outputs. A kilowatt is 1,000 watts. Typically, a household solar system on the roof will put out about a kilowatt, 1,000 watts. That's very typical. A megawatt is 1 million watts. It takes significantly more panels to produce a megawatt. And a gigawatt is 1 billion watts, and that's just panels forever. But it's great. It's making electricity. So now that we have that down, which one will kill me, volts or amps? I don't know.
Oh.
So here's a table telling you what happens to your body when different amounts of currents flow through it. And you can see that it's all in milliamps. Tiny, tiny, tiny amps. You know, threshold of bodily perception, pain with voluntary muscle control maintained, pain with loss of all I've been there. I completed the ground on an ice machine once. That was kind of cool. Severe pain, heart attack. But this is all measured in amps. Milliamps, tiny little amps, parts of amps. So far, it does look like it's the amps that kill you. Pressure or current. We learned this in high school. If you rub your feet on a carpet and charge yourself up to a few thousand volts and then touch a piece of metal, you get a spark and a discharge, but not a lot of pain. It has low stored energy and is over so quickly that it won't kill you. That's what causes every high school teacher in the world to say, it's not the volts that'll kill you, it's the amps. But static electricity situations are completely incomparable to high voltage situations when you are working with electronics. The thing that determines the amount of current flowing through a circuit is the load. If you short out the circuit, you're the load. There can't be amps without volts. And resistance plays a part too. Your skin has resistance. Current doesn't move on its own. It needs energy to move. That's where voltage comes in. Voltage supplies the energy. Your skin has resistance, not a lot, but some. Less if it's wet. However, and here's the kicker right here, as voltage goes up, the skin's resistance goes down. The longer you are exposed to the voltage, the less and less your skin's resistance becomes. The load only draws as much current as it needs at a given voltage. The equation we use is very simple. Here it is, it's Ohm's law. Remember, it's not math. It's a relationship. Voltage divided by resistance equals current. Take the voltage, divide it by the resistance of whatever you are connecting it to, and you will get the current. Remember, not math. Meaning that for any given body of resistance, the more the volts you have, the more amps you'll have. That's why it's misleading to say that it's not the volts that will kill you, it's just the amps. The volts directly determine the amps. So, what does all this tell us about the dangers of electricity? I have a multimeter. I've measured the resistance between my hands, and it reads about 1 milliohm or 1 million ohms. It varies significantly depending on how hard I squeeze the probes or how moist my fingers are. If I were to put my hands on the terminal of a 12-volt car battery, the current flowing through my body would be about 12 microamps, not much. I wouldn't even feel it. If I were to put my hands on the terminals of a 12-volt lantern battery, the current would still be about 12 microamps. The current is the same because the resistance in my hands is millions of times greater than the internal resistance of those batteries. It doesn't matter that the car battery can deliver 500 amps. My hands will only pull 12 microamps out of that battery. A 120-volt wall outlet is a different story. If we were to apply Ohm's law on the 120-volt circuit, about 120 microamps should flow through your body. That's still not enough to do much harm, but people are often killed by household circuits. The reason is that your skin's resistance is not linear. At about 50 volts or so, the resistance of your skin drops dramatically. The current flows through your body may not be limited by skin resistance at all, but by the ability of the voltage source to deliver current. In fact, you can feel a slight tingle at voltages as low as 24 volts. Medical data shows that less than 100 milliamps is sufficient to push a human heart into fibrillation. If the resistance of human skin was linear, if the resistance of human skin was linear, you would have to grab a 100,000 volt current to get 100 milliamps. It turns out that 100 volts is enough. The product of voltage and amps, which is current, remember, is power measured in watts. 1,000 watts will heat the elements in your hairdryer to hundreds of degrees. If 1,000 volts was to push 1 amp through your body, you wouldn't need a hairdryer anymore. On the other side of the spectrum, very high voltage is not necessarily dangerous. The ignition coil in your car or the flyback transformer on your television, old style, will generate over 20,000 volts. If you were to touch either one, it wouldn't be fun, but it probably wouldn't do any serious damage. That's because the output voltage of either of these devices will drop off significantly when you touch the terminals. This is because ignition coils and flybacks have high internal resistance. They can't deliver much power. So what's the answer? Is it volts or is it amps? Basically, it's both. Low voltage, less than 50 volts, won't hurt you because of high skin resistance. High voltage can cause a heart attack if the source can deliver a moderate current, 100 milliamps or more. High voltage coupled with availability of current, like power lines, can result in a lethal shock as well as serious burns and tissue damage. Electricity is an inanimate beast without compassion or remorse. It must be respected at all times. Any questions? Well, that's it then.
The biggest danger is, I guess, that the more grounded you are, the lower the resistance and the faster you'll...
Well, the more, if you have a direct path to ground and your resistance fails after 50 volts, you are the path to ground. And if that source that you're touching can deliver high amps, it will.
That's why you don't want to stand in water during a storm.
That's right.
Or talk on a stage into a microphone.
While standing in water.
Yeah, that's in the rain, in the rain.
I have a question. You often see the electricians on high wires working on repair. Now, at what point are they closing that voltage? And is it from one direction or both directions? And how far do you have to shut it down so that the poor person doesn't get electrocuted?
Right. Well, they don't. They're working with hot live wires up there.
Really?
Yep. And they reroute and they don't touch more than one wire at a time. And they have super insulating things and safety procedures and protocols so that they don't complete a circuit anywhere. If it's really going to be something that they have to like tear it apart and start over, then they go ahead and shut the power off at the grid. But if the guy's coming out because your transformer went blammo, he's just going to wire it up. And he can, because he's only going to work with one side at a time. I have a documentary on that, but it's like an hour and a half, so we can't watch it. But I do have a funny video. Depending on who's in the room, there's some language.
We're all funny. Oh.
It's very funny about what's going to kill you, the watts or the amps, or the volts or the amps. He's very funny. Do we want to watch it?
Yes.
Okay, I warned you.
See how the wire melts and burns under. So the power supply can generate enough current to melt the wire. Still nothing. So I hope I'm clear. Please don't repeat that the current kills, not the voltage. There's a famous saying that goes like this: like, share, and subscribe to my channel.
Two guys nuts.